In the fourth quarter of 2025, TSMC began shipping 2-nanometer chips at commercial volume, not prototypes, not engineering samples, production silicon, moving through packaging lines in Hsinchu, bound for devices reaching consumers within months. This was not supposed to happen yet. As recently as 2021, analysts at Gartner and IBS projected sub-3-nanometer manufacturing at commercial scale was unlikely before 2027. The physics of operating at that scale, where transistor gates measure roughly the width of 10 silicon atoms, were considered too unstable and too dependent on manufacturing precision that didn't exist. The consensus held. Roadmaps slipped across the industry. Then TSMC didn't slip. The node is designated N2. It entered volume production on schedule, matching a roadmap TSMC had published 4 years earlier. In an industry where major node milestones routinely slide by 12 to 18 months, that delivery is structurally significant. The designation 2-nanometer is not a direct physical measurement. It signals transistor density, switching elements packed per square millimeter of silicon. At N2, TSMC achieves roughly 290 million transistors per square millimeter, against approximately 170 million at N5, which powered Apple's A14 chip in 2020. That is a 70% density improvement across 2 process generations. Density is not a vanity metric. Every transistor added within a fixed die area is a transistor that requires no additional power, no additional space, and no additional cooling to operate. At the scale of a data center running 10,000 AI accelerators simultaneously, that arithmetic compounds into billions of dollars annually. AMD became the first high-performance processor manufacturer to enter production at this node. Mainstream media coverage was sparse. The consequences were not widely explained. They should have been. For roughly 4 decades, transistors were built as flat, planar structures etched into silicon. A gate rested atop a channel, controlling current between source and drain. Scaling meant shrinking, tighter tolerances, smaller geometries. Moore's law held because the physical structure cooperated. By the early 2010s, it stopped cooperating. At gate lengths below 22 nanometers, planar transistors leaked current even when switched off. The gate, sitting on one face of the channel, could no longer fully control electron flow. Chips grew hotter, performance gains collapsed. The industry faced a structural wall. Intel introduced the fix in 2011 with its 22-nanometer Ivy Bridge processor, the FinFET, Fin Field Effect transistor. Wrap the gate around 3 sides of a raised silicon fin rather than lying flat atop a channel. Leakage dropped. Electrostatic control recovered. FinFET dominated every major chip generation for the next 14 years, from Ivy Bridge through TSMC's N3 node, which Apple used in its A17 Pro chip in 2023. N2 ends the FinFET era. The replacement architecture is called gate-all-around, using structures called nanosheet transistors. Instead of a fin wrapped on 3 sides, nanosheet transistors stack thin horizontal silicon sheets with the gate surrounding each sheet on all 4 sides. Complete circumferential control. The gate contacts every surface of every conductive channel. TSMC's published specifications show N2 delivers 10 to 15% better performance at equivalent power compared to N3 FinFET, or equivalent performance at 25 to 30% lower power. The trade-off between speed and efficiency improves at every point on the curve. Samsung moved to gate-all-around 1 generation earlier at its 3G AE node in 2022. The transition was troubled. Yields, the percentage of chips per wafer that function correctly, were reported by SemiAnalysis to fall substantially below expectations through the first 18 months of production. TSMC observed, adjusted its development process accordingly, and arrived at N2 with yield performance that early customers have described as competitive for a first-generation node. The architectural shift carried costs beyond the fab. Electronic design automation software from Synopsys and Cadence required complete reconstruction to model nanosheet transistor behavior accurately. Chip designers spent years relearning layout techniques. The tooling investment across the industry reached hundreds of millions of dollars before a single N2 chip entered production. TSMC's capital expenditure for 2024 was $30 billion. The prior year, $32.3 billion. Both figures exceed the annual GDP of roughly 80 countries. This is not an investment spike. It is the baseline cost of maintaining manufacturing leadership at the frontier of semiconductor fabrication. Morris Chang founded TSMC in 1987 with $220 million in Taiwanese government investment. The business model, a pure foundry with no products of its own, building chips exclusively for external customers, was dismissed by incumbents including Intel and IBM as structurally fragile. By 2024, TSMC controlled approximately 90% of the global market for advanced semiconductor manufacturing, defined as chips at 10 nanometers and below. N2 development began in earnest around 2019. The technical obstacles were not incremental improvements over prior nodes. Depositing gate material uniformly around four sides of a silicon sheet 5 nanometers thick, maintaining atomic-level consistency across a 300mm wafer, required manufacturing tolerances without precedent in industrial production. The extreme ultraviolet lithography machines that expose circuit patterns onto wafers, manufactured exclusively by the Dutch company ASML, cost approximately $380 million per unit. As of 2024, N2 requires high NA EUV, ASML's next-generation system, with ASML producing fewer than 20 units annually at peak output. TSMC's N2 facilities required dozens of these machines per fab. The Fab 20 complex in Hsinchu, where N2 volume production began, represents an investment that industry analysts at Tech Insights estimate above $20 billion for its first phase alone. A second N2 facility is under construction in Kaohsiung. A third, TSMC's Fab 21 Phase 2 in Arizona, targets N2 production by 2028 as part of the $65 billion total U.S. investment TSMC announced in 2024. The Arizona expansion carries weight that technical analysis alone cannot capture. N2 production concentrated in Taiwan means 90% of the world's most advanced chips are manufactured on an island the People's Republic of China claims as sovereign territory. The U.S. CHIPS and Science Act of 2022 allocated $52.7 billion specifically to reduce that concentration. TSMC's Arizona commitment is its largest direct response to that policy pressure. Every major AI accelerator deployed at scale in 2025, NVIDIA's H100 and H200, AMD's Instinct MI300X, Google's TPU V5, runs workloads constrained by two variables, operations per second and power consumed to execute them. These variables are not independent. A chip doubling its operation count by doubling power draw is not more useful to a hyperscaler already pressed against thermal limits in its data center infrastructure. N2 addresses both sides of that constraint simultaneously. Greater transistor density means more compute cores, more cache, and more memory bandwidth controllers within a fixed die area. The efficiency improvement from gate-all-around architecture means those additional structures operate at lower voltage without sacrificing clock frequency. For an AI accelerator designed on N2, the combined result is substantially more useful computation per watt. the metric that determines data center economics at scale. NVIDIA's next-generation accelerator architecture, codenamed Rubin, is scheduled for production on TSMC's N2 process. Rubin follows Blackwell, manufactured on TSMC's N3 node and shipping in volume through late 2024. The N3 to N2 transition is projected to deliver performance per watt gains comparable to those seen moving from N5 to N3, a transition NVIDIA's own benchmarks credited with a threefold improvement in inference throughput per rack unit between the A100 and H100. The scale of this matters. The International Energy Agency estimated in 2024 that a single AI inference query consumed approximately 10 times the energy of a standard Google search. With AI inference volume projected to grow 400 to 500% between 2024 and 2027, the efficiency of the underlying silicon becomes an energy infrastructure problem. Based on TSMC's published power scaling data, a workload requiring 100 megawatts on N3 silicon requires closer to 70 to 75 megawatts on N2. That gap determines whether a planned data center can secure a power interconnection agreement from a regional utility. N2 does not solve the AI energy problem. It reduces the rate at which the problem grows. In 2023, the Chinese government issued procurement directives instructing government agencies and state enterprises to replace Intel and AMD processors with domestic alternatives. The policy accumulated across a series of purchasing guidelines collectively known within Chinese administrative circles as the 352 framework, targeting 30% domestic hardware replacement in year 1, 50% in year 2, 20% in year 3. U.S. export controls tightened in October 2022 and expanded again in October 2023, restricted sales of NVIDIA's A100 and H100 to Chinese entities. NVIDIA engineered downgraded variants, the A800 and H800, calibrated below the restricted performance thresholds. Updated rules close that gap. NVIDIA released the H20. The exchange has continued in alternating steps, each restriction producing a modified product, each modified product triggering updated rules. The pattern produced an outcome that mirrors a precedent from mobile software. When US authorities effectively banned Google from providing Android services to Huawei in 2019, Huawei developed Harmony OS, which by 2023 had accumulated more than 700 million registered devices. The ban intended to weaken a competitor instead accelerated the creation of a rival ecosystem. Chip restrictions on China have operated on the same logic, denied access to NVIDIA's top-tier hardware. Chinese AI institutions, including Baidu and Alibaba's Damo Academy, invested aggressively in domestic accelerator development. Huawei's Ascend 910B, manufactured on a SMIC 7nm equivalent process, was assessed in multiple 2024 benchmarks to perform comparably to NVIDIA's A100 on specific large language model training tasks. China's access to advanced manufacturing nodes remains the binding constraint. TSMC is legally prohibited from selling advanced process capacity to Chinese customers under US export rules. SMIC's most advanced publicly acknowledged node as of late 2024 sat at approximately 7 nm in effective density, 3 to 4 process generations behind TSMC's N2, representing 5 to 8 years of manufacturing development under normal industry conditions. That gap is TSMC's strategic position expressed as a number. It is also the central vulnerability in a supply chain where one company on one island manufactures chips that every major AI system in the world depends upon. In 2023, MIT Technology Review reported that 10 billion RISC-V processor cores had shipped. RISC-V is an open standard instruction set architecture developed at the University of California, Berkeley in 2010 and released without licensing fees. Any organization can design a RISC-V processor without paying royalties to ARM Holdings or any other incumbent. The 10 billion core threshold meant RISC-V had already embedded itself across earbuds, hard drives, and AI inference chips, invisibly, without a product launch, without a press cycle. Intel announced a $1 billion fund in 2023 with a mandate that includes supporting companies building RISC-V chips. For a company whose x86 architecture has generated licensing revenue for 5 decades, the directional signal is unambiguous. RISC-V's growth is treated as inevitable. Participation is preferred over opposition. The material substrate of computing faces parallel pressure. Researchers at Peking University published findings in 2026 describing transistors built from semiconductor-enriched carbon nanotubes and bismuth oxyselenide rather than silicon. In laboratory conditions, the architecture demonstrated 40% higher performance and 40% lower energy consumption compared to silicon processors at equivalent design generations. The research appeared in Nature. It is a proof of concept, not a production process, translating laboratory demonstrations to wafer-scale manufacturing with acceptable defect rates historically requires 10 to 15 years. Silicon has held its substrate position since the 1950s, not because alternatives lack merit, but because the industrial infrastructure surrounding silicon, purification, etch chemistry, doping, packaging, represents trillions of dollars of accumulated industrial capability. Displacing it requires a better material manufacturable at scale, using tools buildable at industrial volumes. Bismuth-based transistors do not yet meet that threshold. The physics confirm the direction. What distinguishes the current period is that 3 separate foundational transitions are running simultaneously. The move from FinFET to gate-all-around at 2 nanometer is the deepest transistor architecture change in 14 years. RISC-V represents the most significant open challenge to proprietary instruction set architectures in 2 decades. Laboratory silicon-free transistors challenge the substrate that has defined computing hardware since its inception. None of these transitions are waiting for the others to complete. TSMC began shipping N2 chips in Q4 2025. AMD placed its processors on that node first. The AI infrastructure consuming those chips at scale is now entering a hardware generation that the data centers built in 2023 and 2024 were not designed to accommodate. The compute requirements of the models being trained today assume efficiency levels that only became physically available in the final weeks of 2025. The barrier broke on schedule. The era it opens has no scheduled end.